All right, let's talk about the one question that can make or break a system design interview. How do you actually scale a system? How do you go from 1,000 users to 10 million? It's a question that stumps so many brilliant engineers, mostly because the most common answer completely misses the point.
So picture this. You're in the interview. The pressure's on, and you drop this line. And hey, it sounds good, right? It's a standard, well-known technique. You just add more copies of the database to handle more people reading data. Simple. But then you look over at the interviewer, and nothing. They are totally unimpressed. So what went wrong?
Because that answer, well, it only solves the easy part of the puzzle. It's kind of like saying you're going to win a marathon by training for the first 100 yards. Scaling reads is, frankly, the trivial part. The real test, the thing that separates a good engineer from a truly great architect, is understanding how to scale the other, much harder side of the equation.
And this gets us to the absolute core of the misconception. See, scaling isn't just one problem, it's two, and they are completely different beasts. The real challenge, the thing that keeps architects up at night, isn't figuring out how to handle more people looking at stuff. It's handling more people changing stuff.
The difference here is actually pretty simple, but it is profound. A read is a passive action. It doesn't change a thing. You're just looking. But a write actually modifies a shared reality. It changes the state of the world for absolutely everyone. And that, right there, is where all the brutal complexity comes from.
So, let's break this down. Why is one so incredibly easy and the other so notoriously hard? Well, it all boils down to one key idea: coordination. Think about it like reading a newspaper. 1 million people can all read the exact same front page and it doesn't change the news one bit, right? It's the same with data. Reads don't alter anything. So you can just make more copies, caches, read replicas, and serve more and more users. We actually have a great term for it: embarrassingly parallel. You just throw more machines at it and boom, you get more capacity. It scales horizontally, almost perfectly. Writes, on the other hand? Oh man, that's like trying to get 1 million people to edit that same newspaper front page all at the same time. It's just chaos. Every single writer is changing the truth. So all of a sudden you need rules. You need things like locks to stop people from editing at the same time, and transactions to make sure changes happen correctly. Without that stuff, you get these dreaded race conditions where the final result is just wrong. This chaos is why adding more writers doesn't just add capacity, it adds complexity, and a lot of times it's exponential. And all of that complexity, all of that chaos, it really boils down to one single fundamental bottleneck. And I mean it. This is the key insight. Once you really get this, it will change how you look at system design forever. And that concept is called serialization.
See, to avoid that chaos we were just talking about and to keep our data from getting corrupted, writes simply cannot happen all at once. They have to get in line. They must be put into a single ordered sequence, one after the other. This process, this serialization, is what guarantees that changes happen in a predictable way.
And here's the thing you have to understand. You can't just optimize this away with some clever code. This is not a software bug you can fix. It is a fundamental constraint. It's almost like a law of physics for distributed systems, right? You can't have two things occupy the same physical space, and you can't have two writes modify the same data at the same time without a clearly defined order. Let's make this super concrete. Imagine a bank account with $100 in it. Now, two different payment requests for $50 arrive at the exact same instant. Without serialization, both of those processes could read the balance as $100, both of them subtract 50, and both of them write back a new balance of $50. The bank just lost $50, and the customer is furious. That is a race condition, and it's exactly why financial systems have to get serialization absolutely perfectly right.
So if every single write has to get in one single line, how in the world do services like Google or Facebook even exist? Well, they kind of cheat. They find a clever way around this single global line by breaking the problem apart, and they do it with a technique called sharding.
I love this analogy. Instead of having one massive journal of truth, where every single transaction in the world has to be written down perfectly in order, what if you had 1,000 smaller journals? A write for user A goes into journal number 1. A write for user B goes into journal 427. Now, they're not competing for the same spot in line anymore. They can happen at the same time, in parallel. This, in a nutshell, is sharding.
But remember what I said, there is no free lunch. By breaking our one big journal into 1,000 little ones, yeah, we solved the serialization bottleneck, but we've just created a whole new set of really hard problems. Like, what if user A needs to interact with user B's data? How do you move data around if one of those journals gets too full? Sharding is incredibly powerful, but it is a massive architectural commitment.
And that right there is the absolute key takeaway. Scaling rights is always a trade-off. You are trading the beautiful simplicity of a single source of truth for the raw performance of a distributed system, and you pay for that performance with a giant increase in complexity.
So let's go all the way back to that interview room. When you get asked how to scale, the architect-level answer is this. Reads and writes scale differently. Reads are easy, we can just fan them out with replicas. The real challenge is writes, because they modify a shared state, and that requires serialization. So we're going to have to manage that bottleneck, probably through a strategy like sharding, and we have to be really mindful of all the complexity that adds.
So as we wrap this up, let me just leave you with one final thought. Think about booking an airline ticket, or making a purchase online, or even just sending a simple text message. These are all right operations. Every single one of them is modifying a shared reality, and they have to be right every single time. And now you know exactly why that is such an incredibly hard problem to solve at scale.